Welcome to our discussion of buffers today. What we're going to talk about today is what a buffer is, how they work, as well as I'm going to show you how to calculate the pH of a buffer using equilibrium calculations. In future videos, we'll learn an easier way of calculating the pH of a buffer, but for right now, we'll work with equilibrium. So this first slide, we're going to talk just really quickly about what a buffer is and how to prepare it. And then in the following slides, we're going to really discuss why it works as a buffer. So let's get started. So a buffer basically is any solution that resists changes to its pH when an acid or base is added. So basically you'd add some acid to a solution and you would expect, okay, so the pH is going to go down by however much because I added so much acid. And with a buffer, what will happen is the pH will go down, it'll get more acidic when you add an acid, but only by a little bit, much less than you'd expected. And that's its buffering effect. So it resists changes to its pH. And we make buffers by adding a weak acid with its conjugate base, or by mixing a weak base with its conjugate acid. So if we do that, we're going to get this buffering effect. And in the next slide, we'll talk exactly about how that works and why that works that way. So for example, if we add sodium acetate, which is the conjugate base of acetic acid, to a solution of acetic acid, we would have a buffer. And again, we'll talk in the next slide about why that works. Okay, so let's look at the example of hydrofluoric acid, which is a weak acid. Its Ka is 3.5 times 10 to the minus 4. And here's our acid dissociation for hydrofluoric acid. Now we know because this is small that the equilibrium lies to the left. So it favors this side of the reaction. So if we were to draw a graph here, let's draw a graph of concentration. Right? And this side will be our different stuff. So here we have HF concentration, and that's going to dissociate into H plus and F minus. Now, of course, H3O plus is the exact same thing as H plus. So those two things are equivalent. This is that same equation. And if we start our reaction and we put in a whole bunch of HF, like this, so we have a huge concentration of HF, well, right away, this HF is going to dissociate some. Not very much because this is a small number. So right here, this part breaks off and it creates that much H plus and an equivalent amount of F minus, because for every one of these that breaks, you get one of these and one of these. All right, so that is our equilibrium is set up now. We started with a bunch of HF, put it in some water. Some of it broke apart, not very much, but that's where we lie. So let's look now at what happens when we add a base to the situation. So let's say that we make this solution and we measure the pH to equal 3. That means the H plus concentration is equal to 10 to the minus pH, so 10 to the minus 3, or 0.001 molar. And if we have, I don't know, a 1 liter solution, that's 0.001 moles of H plus to make this pH. So we can say that what if we add NaOH? And specifically, what if we add 0.001 moles of NaOH? Well, we know in a 1 liter solution we have 0.001 moles of H plus because our pH is a 3. So if we add this much NaOH, we should go from a pH of 3. So our pH should go from 3 up to 7, because we should fully neutralize it if we add this much, ignoring all of this stuff. But if we just had just this in solution, we add in the same amount of OH, it's going to fully neutralize all the H plus. We'll go from a 3 to a 7. So what happens? So when we do dump in this 0.01 molar, sure enough, all of this gets chewed up by that, by the sodium hydroxide. There's no H plus. So we can think of maybe the pH instantly going down to 7. But what happens right away, as soon as this H plus is diminished here, we are taking products out of the reactant, which is going to shift the equilibrium, out of the reaction, I should say. When we take away this H plus, it's going to shift the equilibrium from the HF towards the products, towards the right. So we essentially, this HF here replenishes some of the H+. So some of this will break apart right here. This will dissociate, and we'll end up with replenishing the H+. So we'll add in 0.001 moles of sodium hydroxide, which we'd expect to neutralize the solution, but because we have extra hydrogen that's bound to the F- here, extra H+, then it's going to dissociate and replace some of the H+. We only go from 3 to, say, 3.2 of a pH. So we did increase, right? So our solution became less acidic because we added base, but not by nearly as much as we thought. And that's that buffering capacity. So whenever there's this extra bound up H+, right, it's bound to the F-, so it doesn't count towards being an acid, and not until it dissociates it does. Whenever this extra like reservoir of H+, if we use up H+, it'll replenish it and replenish it. Now if we keep doing this, we keep adding base, again, this will break down. More will come out. Each time less. And then once we're out of HF, its buffering ability is gone, and the pH will then increase very, very quickly instead of slowly. But as long as we have HF on here, we're going to be able to buffer it somewhat. Okay, that's awesome. So a weak acid all by itself is actually a pretty good buffer against adding bases. It keeps the concentration the same. Now what if instead, let's look at this graph here and say, what if instead we were to start again with our large amount of HF, and then we have here H+ and F-. And again, before we add anything, the equilibrium sets up, so some of this breaks off and creates a small amount of H+ and an equal amount of F-. Now what if instead of adding NaOH, we add HCl? So now we're adding in a bunch of H+ ions, so suddenly this jumps up. So we get a lot more H+ in here. And of course, what happens when you add products to an equilibrium, the equilibrium shifts to the left, making more reactants. So these guys are going to shift this way and create more HF. So we're going to lose a little F-. And for every F- we lose, we're going to lose an H+. And then these are going to shift over, and it's going to gain, I'm going to draw off to the side here, it's going to gain a little bit of HF. So now we have a little more HF in here. So our pH here is going to decrease. So it's going to get more acidic because we're going to have more H+, but not by as much as we expect. Now here's the problem with this. This is a really small concentration, so this shift can't shift by much. So while a weak acid is a good buffer for bases, it's a really bad buffer for acids because there just isn't much reservoir of F- to react with the H+ and drive it backwards. All right. So then the question is, well, then how do we make a weak acid a really good buffer for acids? Let's take a look. So if we come down here and we say, okay, so, whoops. Let me erase that real quick. So if we come down here and we take another look and we say, all right, so now let's go back to our initial situation where we had a big concentration of HF, and then we had H+ and F-, and a little bit of it breaks off, creating a little H+ and a little F-. And we said it's a really good buffer. This is a really good buffer for bases because there's all this extra reservoir of H+ that can be dissociated to replenish the H+ that gets used up. So we have this large amount here. But it was weak for acids because there's not a lot of F- to run the reaction backwards to consume extra H+ that's added. So the solution here is we add F-, and to do that we have to add something like sodium fluoride. So when sodium fluoride dissolves in water, it breaks up into Na+ and F-. And this F- is going to suddenly jump the concentration of F- way up like this. Now, of course, when we do that, it's going to drive this reaction in the reverse because we increased here, but there's not a lot of H+, so it's not going to drive it very far. It's going to drive it down to like here. This will get eaten up, and this will get eaten up, equal amounts, and that will make a little bit more of this one. So it'll win back some of that. that we lost earlier. Let me erase this first one real quick. So now here's our situation we find ourselves in. And now this one can be a good, there's a lot of extra H plus in there, and it's bound to the F minus, so it can make more H plus if it needs to, we add a base. So it's a good buffer for a base. And this way, it's a good buffer for an acid because now we have lots of F minus in solution as well. So if we add extra H plus, the F minus will bind to that H plus, turning into HF, but taking it out of solution, so it controls our pH. So here, this is a good buffer for both. Good buffer for acids or bases. And remember, we got there by taking a conjugate acid and adding in its conjugate base, adding in more F minus. Now, ideally, a really good buffer, so buffers are at their best when it's a 1-to-1 ratio here. So when these are equal concentrations, the F minus and the HF are equal concentrations, you get the best buffer you can for that concentration. And then the other thing we can do is we want to try and up this concentration as much as we possibly can together. So we want to get them both up really, really high. That way there's a lot of room here a lot of reservoir here of H pluses that are bound to F, as well as a lot of F minus here to soak up extra H plus when they need to. So the higher the concentrations, the better they are, and the more equal the concentration between HF and F minus, the better the buffer is. All right. Now we focus so far only on weak acids. The exact conversation happens with bases, except it's just everything is flipped. You can think through that one on your own. But let's take now, what would happen if we looked at, instead of starting with a weak acid, what if we start with a strong acid like HCl? So the HCl is going to dissociate fully into H plus and Cl minus. So if we start with a bunch of HCl and we let it dissolve in water, well gosh, all of this is going to fully break up and make that equal amount of H plus and an equal concentration of Cl minus. And these two are equal to your starting HCl. But notice there's no reservoir here of unbound H plus. So basically all the H plus is in solution. So now if we add NaOH, so we add some hydroxide ions, it's going to chew up a bunch of our H plus ions. So let's say we add that much, we chew up this much. Well, there's no undissociated H plus over here to replace those that were lost. So we're just going to lose them. This is going to be completely non-buffered because there's no reservoir of bound up H plus to replace. Now you might say, oh, but what if we add H plus to it? So we add some acid to it and we suddenly jump this up really, really high. So we jump it up way up here like this. You might think, oh, but look at all the Cl minus that can bind on to run the reaction backwards using up some of that H plus. The problem is Cl minus is an extraordinarily weak base because this is a really strong acid. So really Cl minus does not stick to H plus. So again, even when we add acid, we get the effect we expect. It's not a minimized effect by the buffer. So strong acids, strong bases, and strong bases are not buffers. And that's a good point to have. And this text here I think just kind of follows along. So if we add sodium fluoride, so that was at this part here. When we added the sodium fluoride, drives equilibrium to the left, which results in a less acidic pH. So we've lost some H plus here. We've become more because we've added a conjugate base. And it is now a buffered solution. You have a reservoir of F minuses that can sop up any extra H pluses in there, turning them into HF. Or if you lose H plus by adding a base, you've got a bunch of extra H's that are bound to F minus that can dissociate and replace some of those. And that's how a buffer works. And that's why it's important to have a weak acid with its conjugate base or a weak base with its conjugate acid. Try this comprehension check real quick. So for each of these, I want you to discuss whether each of these is going to be a good buffer or a bad buffer, and then kind of explain your reasoning on each one. So go ahead and pause the video, take a chance to kind of write down some of your thoughts on these, and we'll start up in just a second. All right, here we go. So we have 0.1 molar HCl, and we're mixing it with 1 molar NaCl. And you're like, okay, so the conjugate base of this acid is Cl minus, and we're adding Cl minus, so maybe that's going to be a good buffer. But you have to remember, oh wait, this is a strong acids, and strong acids fully dissociate, so they have no buffering capacity at all. So this is a no good. No good. Strong acids are not buffers. They have no ability to stop the pH from changing. All right, and then this next one is we have 1 molar H2CO3 with 1 molar NaHCO3. The first thing is figure out what's the conjugate base of this acid. So if we break off a proton, our conjugate base would be HCO3 minus 1. And sure enough, if these two broke apart, you'd have an Na plus CO3 minus in solution. They would break apart, HCO3 minus. That's the conjugate base, and we're like, yay, that's a good buffer. And we also notice that, look at this molarity. That's a relatively strong molarity. So this is going to be a lot of reservoir of both H plus and HCO3 minus that we can use. So this is going to be a very good buffer. And then down here we look at, 1 molar HCN. We're like, okay, so this is a weak acid. The conjugate base is CN minus, but we're not adding any extra CN minus. So this will actually, and this is fairly strong, this will be a pretty good, buffer for bases, but not a good buffer for acids. So this is a poor buffer. Right? So we do need the acid with its conjugate base to make a good buffer. Or more about buffer, missing the conjugate base. Okay? So this breaking apart would make very little CN minus on its own, so it wouldn't be able to counter any H plus addition. It'd be a very bad buffer for acids. And a buffer has to be good for both. It's got to resist both of them, be a good buffer. And this last one, 1 molar HCN with 1 molar NaCl. All right, so here our conjugate base again is CN minus. Now over here we're going to give Na plus and Cl minus off in solution. Neither of those ions are going to be the conjugate base of this one. So this is also a poor buffer. Cl minus is not the conjugate base. Of HCN. And again, to get a good buffer, you need both the weak acid and the conjugate base. All right, so that does it for our discussion of buffers. I hope that was helpful.